a very basic hypothesis testing. So today we'll show you the two different cases, and we'll start doing a lot of exercise altogether. Okay, so last time, if you cross-reference this procedure with your textbook, you'll see your textbook has further divided into 7 or 8 different steps. I like to simplify it into 5 steps. Let's go over those 5 steps. First of all, you need to know what is our parameter of interest. For our lecture, all we're focusing on is population mean. Second steps, based on the problem description, write down your H0, 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 and H1. Null hypothesis and alternative hypothesis. Null hypothesis is usually what we believe the current process is. While alternative hypothesis is what we're trying to prove. Okay, so our result is either fail to reject the null hypothesis, which means the current process is still true, or we reject the null hypothesis and prove that my alternative hypothesis is true, that something has changed in my current process already. Okay, step 3, establish your rejection criteria and find your critical value based on alpha. Alpha has to be given to you. In your project, you decide what is the alpha in your project. 0.05 is typically fine with the majority of the analysis. Step 4, calculate test statistic. Test statistic is based on your sample average. And then we'll show you how to draw conclusion in 2 different ways. First way is to compare step 3 and 4. Compare where you store sample average, your actual data located in respect to the confidence interval established in step 3. We'll also show you the second way by calculating the p-value. Okay, so it's a quick review of what we've covered last time. Let's go down to it. So now we're going to teach you 2 different cases today, just like chapter 8 with confidence interval, 2 cases. When the population variance is given, we'll use the Z distribution. Okay, and this steps is only applied to step 4. You can see I highlighted step 4 on the right hand side. That's the only differences. Okay, when population variance is given, we're going to use the Z statistic in step 4. Let's look at this case. They've set up the alternative hypothesis as a 2-sided hypothesis testing. Okay, so this is a 2-sided. So in my step 3, there's going to be 2 critical value and 2 rejection criteria. So I'm going to sketch it. So this is a Z distribution. We've set up as a 2-sided. H1, that means does not equal to a value, which means this is a 2-sided. Okay, so here we have 2 values. Okay, so this is my first critical value, Z alpha over 2, and positive Z alpha over 2. Okay, when will we reject it? When my test statistic is located outside this confidence interval, we reject the null hypothesis when my test statistic is greater than the critical value on the right hand side, this part, or it is below the lower bound, this side. Okay, that's when we reject it. That means our sample information is inconsistent with our null hypothesis. Our null hypothesis believes our population mean should locate it between these 2 critical values. That's how we establish a confidence interval. But based on the actual sample we've collected, it actually tells us the sample mean is not located inside there. So that's the inconsistency. Because of that, we are going to reject the null hypothesis. Or if my sample statistic is located within this confidence interval, in other words, it's located somewhere around here. So this is what we believe our process is, and our actual sample confirms that the information is consistent. If that's the case, we fail to reject the null hypothesis. In other words, we concluded null hypothesis that our actual process is exactly the same as how we established it. Okay, two different ways to draw a conclusion. Let's take a look at an example. Okay, send me a chat or raise your hand if we're going too fast and you don't understand how do we get there. It's really important in the next an hour 40 minutes that you really understand each step. There's only 5 of them. Okay, let's make sure you will come out of this class knowing exactly how to perform those 5 steps. There's some details here and there, and we'll go down to each one of them. If any of the details is not clear to you, feel free to stop me and ask questions. All right, let's look at this question. Now we're testing a escape system, and it is powered by a propellant. So the important characteristic is to test the burning rate of this propellant. Okay, the burning rate is an important product characteristic of the propellant. What does the specification say? The specification says the burning rate must be 50 centimeters per second. Okay. What else is given? Population standard deviation is given. That's my population standard deviation. My alpha is also given. Alpha is 0.05. And then we're going to go ahead and test 25 actual samples from this process. Based on this result, we're going to verify if this claim is true, if our current process is still meeting the specification at a burning rate of 50 centimeters per second. So let's collect 25 samples, and we've tested them. Their average sample burning rate is 51.3. That's fairly close to 51, but not exactly 51. Can we perform a hypothesis testing to see if this sample is coming from a population? That the population means exactly 50. So that's what we're going to do for the hypothesis testing. Again, we're going to perform a hypothesis testing and see if this 25 sample is coming from a population that the population mean is exactly 50, which is what we want the product to be, exactly at 50. So let's start a hypothesis testing. I'm going to use the 5-step method. Hypothesis testing, HT stands for hypothesis testing. Step 1. Define our parameter. What is our parameter of testing here? We're testing the burning rate. Okay, so our burn rate. Step 2 is a critical step. We are going to write the null hypothesis and alternative hypothesis. This is critical because you really have to set up this step right in order to carry the rest of the calculation correctly. So H0 is what we believe the process is. What we believe is that our current process is meeting the specification, is exactly 50. Alternative will prove it otherwise. If our process does not meet the specification, that means the mean is not going to be 50. Could be higher, could be lower, but it's not 50. My process has shifted. Okay? Now, a lot of students will come back and ask me, my sample already tells me it is 51.3. It is not 50. Why do we still need to perform the hypothesis testing? Okay, so I want you to understand this problem from a population perspective. So here is my population. I have a lot of samples over here, right? But there's only one population in which we do not know of. So what can we do? We are collecting some random samples in here. In this case, we've collected 25 of them. So their average is 51.3. What we don't know is, if we collect another 25 sample, is it still going to be greater than 50 or less than 50? So when you have a population mean of 50, we can have a confidence interval when we use to estimate the population mean. My sample mean could be here. I could collect some sample and get a sample mean over here. I could also get a sample, collect a sample and calculate sample mean here. Sample mean 1, sample mean 2. Or when my population mean is not 50 anymore, let's say my population mean is actually over here. If that's my actual population, my actual sample mean could end up being here. This location is outside this confidence interval that we've established. Okay? So based on the sample information, it's going to tell us the actual population is exactly what we believe it is, or it is not. Okay, that's why we're performing analysis. Sample mean only tells us part of the information. We really have to go back and compare that sample mean to the confidence interval to see if it's still coming from a population with a mean of 50, or it's actually coming from a population that the mean is not 50 anymore. Okay, so do not confuse sample average to the population average. Okay, population average is the big picture. Sample average is only a part of the population. All right, so we cannot simply pick 25 samples and draw a conclusion from there. Okay, we have to consider the variability of collecting sample biases. All right, so just want to put it out there. Let's continue. Step 3. Oh, first of all, based on the way we write the alternative hypothesis, this is a two-sided hypothesis testing. Or, in other words, we're going to create a two-sided confidence interval. Now, step 3. Based on our alpha is 0.05. Do we know the population standard deviation? Yes, population standard deviation is known. We're going to use the z distribution.
Professor, I have a question.
Go ahead.
Do we ever use a one-sided?
Yes.
We use it? Okay.
Yeah. So just like the confidence interval, okay? You've calculated one-sided confidence interval or two-sided confidence interval. Exactly the same with hypothesis testing. We can perform a two-sided hypothesis testing. We can also perform one-sided hypothesis testing. Okay, so we're going to go through some exercise later on, and we'll show you each case.
Professor, the one-sided hypothesis, when you're ever going to get the t-value, is it just the alpha?
Yes.
Just the alpha itself, not divided by 2, correct?
That's right.
Okay. I want to make sure on that.
Yeah. Okay. Okay. So in step 3, we are going to calculate our critical value. In this case, values, since we have 2. And over here, I'm going to sketch it. You will get used to this because I'm going to sketch it so many times, and hopefully you have the sketch in your mind. So we know this is a z distribution because standard deviation is given, right? Here are my two-sided. How do I know it's two-sided? Because the way we write our alternative hypothesis. How do we establish the confidence interval? Here, two-sided, alpha is 0.05. This part has probability of alpha over 2, 0.025. This part also has probability of 0.025. So Critical value on the left-hand side is negative z-value with cumulative probability of 0.025. Positive critical value, z-value, with the exact same value on the negative side, 0.025. Okay, so those are my two critical values. And we've used this value a lot, actually. If you can remember that by now, these two critical values are plus minus 1.96. If you don't, at least you know how to find it. Go back to your Z table or go back to your Excel to find it. Okay. So based on this critical value, where is my reject area? Okay. My reject area is at where will be the area for us to draw the conclusion to reject the null hypothesis? In other words, where do we find the sample information inconsistent with our hypothesis testing? When the sample information is outside the confidence interval, right? So the plus minus 1.96 is my confidence interval. I'm going to put them over here. Plus minus 1.96 is my confidence interval. When it is outside this confidence interval, we will reject the null hypothesis. So when my Z test statistic falls below the negative lower bound, negative 1.96, or when my test statistic is greater than positive 1.96, it's either located on this side or located on this side, outside this confidence interval. All right? Step 4, let's calculate the test statistic. How do we derive the test statistic? That slide's on top. I'm going to rewrite this one more time. This is how we derive the test statistic. I'm going to write this one more time. This is from our sampling distribution. If you don't know how do we derive this, go back to your chapter 7, sampling. This is when we add the sample size into our equation. Okay. Okay, I'm going to rewrite the equation over here. My test statistic, Z naught, is sample average. Subtract what we believe the population mean is, divided by population standard deviation, divided by square root of n. Our sample average is, let's see, where's my sample average? 51.3 here. This is my sample average. That's my sample. That's my population standard deviation. Okay, 51.3 subtract hypothesis value. We believe our population mean is exactly 50. Standard deviation 2 divided by sample size square root of 25. Okay. This value is 3.25. Now let's compare the location of my test statistic to the confidence interval, 3.25. 3.25 is not located between plus minus 1.96. It is actually somewhere over here, 3.25, outside the confidence interval. So do we meet the rejection area? Yes, we do meet the rejection criteria. Number 5. My test statistic is outside the upper bound. As a result, we reject the null hypothesis. Conclude alternative hypothesis. That means it's not equal to 50. Typically, this is where we stopped, but I will personally emphasize you to interpret this result. What does that mean when we reject the null hypothesis? What does that mean to this question? Let's go back to this problem description one more time, and I'll explain why this is important. We're trying to prove if our process is meeting the specification. If it does meet the specification, mu is 50. This means we meet the specification, right? Meet specification. If it does not, our alternative hypothesis tells you it does not meet the specification. And that's what we're concluding, right? So I want to put this one more time over here. The burning rate does not meet the specification. This is the most important thing. That's why we're performing this analysis. If you recall last week, one of the most important things in inferential statistics when we're performing hypothesis testing or confidence interval is that it helps you to make an informed engineering decision. What will you do as an engineer? You'll perform this test. You actually go ahead and collect data from your production, do all of this average, calculate all this average, and perform this analysis, and report this to your manager. What is your manager going to see if you don't put this conclusion there? Reject null hypothesis? What does alternative hypothesis mean? What does that mean? What he was expecting to see, what your manager is expecting to see, is that your analysis shows the current burning rate does not meet the specification, so that your manager can make a decision to reject this lot. This lot is not good enough to meet the specification. We have to reject this lot to find out if there's any way we can rework around it and bring it back to meet the specification, or has there any process shift in your process that's causing this result, and more improvement, more engineering analysis needs to put into place. So this is an important decision-making point. There's a whole lot of decision-making strategy is going to be based on this result. So I want you to be able to write this down in the way that supports your manager or supports you to make a decision. Okay? So very important, I want you to write down the interpretation. Okay? Now, so I will ask you to write this interpretation for all of your projects. Okay, I will turn it back to you and ask you to do that again to add the conclusion, to add the interpretation of all of your hypothesis testing. Now let's go back to here. Previously, we know there are two different ways to draw conclusion. The first one is what we just showed you. You draw conclusion by comparing the test statistic to the critical value. Now I want to show you how do you derive p-value and draw conclusion based on p-value. P-value at this point will seem complicated, but there's a lot of application when we go to chapter 10. So we're building a foundation for chapter 10. Okay, let's look at p-value. I'm going to resketch this part and only focus on our test statistic because p-value, sorry about my messy handwriting. P-value is calculated based on your test statistic. Okay, so I'm going to sketch this part one more time and we'll only focus on the test statistic. This is my Z. And this is my test statistic. This value is 3.25. What is p-value? P-value is how we quantify this test statistic into probability under this bell curve. It's this green highlighted area over here. We know the area under this probability function is a probability. So let's calculate this area. Okay. And don't forget, since this is a two-sided hypothesis testing, I have my alpha on both sides. Okay, so I will also have my p-value on both sides. In other words, here, this stands for half of the alpha. In other words, this is also half of the p-value. All right, in a two-sided hypothesis testing. So my p over 2 value is, how do we derive that value? Now we're back to chapter 4, the basic calculation of a normal distribution. Okay, it is the probability of my z statistic greater than 3.25. Okay, just because we move on from chapter 4 doesn't mean we will not use the probability we learned from there. How do we calculate this value? I am going to use 1 subtract the cumulative probability from negative infinity all the way to 3.25. All right? And actually, let me see if I can derive that value. $3.25. I don't have it anymore. There we go. So that value is 0.0057. Okay, at this point, I won't go back to show you the z table or the Excel to show you how to derive this. You should know that at this point. Okay, so my p-value is this value 0.00057 multiplied by 2. Okay, the reason this is a p over 2 is because this is a two-sided hypothesis testing. So always be clear about if you're doing a one-sided or two-sided testing. Okay, so my p-value is this multiplied by 2.001154. Okay, what are we going to do with this p-value? We're going to compare the p-value to, what is the other probability we also have? Alpha, right? Alpha is how we establish the confidence interval. It also tells us the probability of rejecting the null hypothesis. Is our alpha greater than or less than the p-value? Let's go back to here. Okay, this is our z value. This is our z statistic. My upper bound of the confidence interval is located on the left-hand side of the test statistic, which means this area under this bell curve will be greater than my p-value. Okay, so my alpha is actually over here. If we can put it into a perspective, this is alpha over 2. This value is 0.025. My p over 2 is 0.00057. Oops. 0.00057.
Professor, alpha goes into p half, right? Does it take part of it as well, or just that piece that you colored red?
That's what I color red is half of the alpha.
Half of alpha, okay.
So compare my p-value to alpha. My p-value is less than alpha. Okay? P-value less than alpha means my z-test statistic is located outside the confidence interval. That's the only way to have my p-value less than alpha. Again, my p-value is less than alpha. The only way for that to happen is when my z-test statistic located on the right-hand side of my test statistic, positive z.025. Okay, that's the only possible way to have my p-value less than alpha. In other words, when p-value is less than alpha, we reject the null hypothesis and conclude the alternative hypothesis. Now, if this part is not clear to you, I want you to go back and do the sketch just like how I did it here. Just like how I did it here. Then it'll make more sense to you. Okay? The z statistic and z critical values are the value on the z-axis. P-value and alpha are the area under this bell curve line, which represents probability. Okay? So this result should correspond to another way we did earlier. Reject the null hypothesis, reject the null hypothesis, conclude alternative hypothesis, conclude alternative hypothesis. So does it matter if you use the first method, compare the test statistic to critical value, or the second method, compare p-value to alpha? Both will come to the same conclusion. Okay, I'll give you a minute to write this down. And also elaborate more, why is this important, since it seems complicated. The beauty of this is that simply compare p-value to alpha. And you know what is alpha. Alpha is already given to you. You can draw a conclusion fairly quickly, and in Excel and also in Minitab. You can skip the step of calculating the test statistic and simply look at your p-value and compare to alpha and draw your conclusion. When p-value is less than alpha, we reject the null hypothesis. When p-value is greater than alpha, we fail to reject it. This becomes really helpful when we have more than one population mean. I'll give you an example. Some students like to see what contributes to their GPA. They like to divide it into number of units they're taking, number of hours they study, or how much time they spend on extra curriculum. So if you can have all of those separate aspects and perform hypothesis testing on all of them, you can simply look at their p-value to know if each aspect contributes significantly to your GPA. The p-value allows you to look at multiple population means at the same time and perform analysis all at the same time. So one hypothesis testing, multiple population means. This becomes very efficient. Well, so I'll just leave it like there, and we'll go back and explain more in chapter 10. Okay, in chapter 10, we are going to perform hypothesis testing on multiple parameters. Any questions so far? Feel free to put your question in chat or raise your hand. Okay, if not, let's go to our second case. Our second case is very similar to your confidence interval. Second case is when the population mean is not given. When population mean is not given, okay, we use t statistic instead of z statistic. Okay, and the only difference is that we're going to use the sample standard deviation instead of population standard deviation. Since in this case, population standard deviation is unknown. But you can always go ahead, collect sample, and calculate the standard deviation of your sample. Okay, so here gives you a different ways to construct a hypothesis testing. The same rule applies to the first case when a population variance is given. You can form a two-sample hypothesis testing when you write your alternative hypothesis this way. This means it's a two-sided. And I want to slow down by sketching each case to you so it's more clear to you. So let's look at the first case. when I write alternative hypothesis is that mu does not equal to a value of mu 0. That means this is a two-sided. In other words, this is my t distribution. Okay, I'm going to have a lower bound and the upper bound. The lower bound is going to be negative t alpha over 2. Don't forget one more parameter associated with t distribution. That's your degrees of freedom, sample size minus 1. And the positive critical value is t alpha over 2. Same thing, sample size minus 1. Okay, so where is my rejection criteria? When my test statistic is located greater than the upper bound, that this area corresponds to this part, or it below the lower bound, which is this area over here, which is this part. In these two situations, we will reject the null hypothesis. Reject null hypothesis. Reject. Okay. And what happened if it falls between those two confidence interval? Two critical value of the confidence interval? We fail to reject. Okay, hopefully that puts it into perspective and you can understand it better. Now I want to slow down and look at the second case. And I like to associate them, each one of them, with a graph. Okay, when I write my alternative hypothesis as my mu greater than a mu naught, that means this is a one-sided upper bound hypothesis testing. So I'm going to sketch it here. This is my T. This is my sketch. One-sided upper bound. That means my critical value is right here. What is the probability greater than here? It's not alpha over 2 anymore. It's alpha since it's one-sided. Okay, so this critical value is positive T, probability of alpha, degrees of freedom, and minus 1. Okay, so when will we reject the null hypothesis? We'll reject the null hypothesis when my test statistic is outside the confidence interval. This area, outside the confidence interval. Okay, so when my test statistic is greater than T alpha n minus 1, this area will lead to rejection of null hypothesis. If it's below, we fail to reject. Last case, less than. Less than is still one-sided but lower bound. Okay, so third case, when this is alternative. Alternative is written as my population mean less than a mean. This means it's a one-sided lower bound. Hypothesis testing. Same thing, I'm going to sketch a T distribution. Sketch it. In this case, I have a lower bound. What is the probability below this lower bound? Alpha. So this critical value is T, negative T, probability alpha, degrees of freedom n minus 1. What is my rejection criteria? When my test statistic is located below this critical value. So this area, below this area, will lead to rejection of my null hypothesis. In other words, if my test statistic is located inside the confidence interval, inside means greater than this lower bound, and we fail to reject null hypothesis, which is here. Okay, I want to put each criteria into perspective so you know all of the possibility. When you're not sure, sketch the distribution just like how I did it, whether it's a z distribution or a t distribution. Sketch it, highlight the critical value, then you should be able to see pretty clearly where is my rejection criteria, where's my confidence interval. If outside the confidence interval, that's my rejection area. Okay, I put a lot of time in this lecture to sketch it because I want you to have a perspective related to the actual distribution. So you shouldn't have to memorize anything, and you should be able to draw your conclusion based on your sketch.
Professor, sorry, the middle one, the second graph, is it H naught or H
Here, right?
Yes, yeah.
H1.
H1. Okay, I thought it was H. Okay, thank you.
I was trying to correct it. Turned out make it more confusing. Yeah, you're right. Thank you. It's H1. That's the only hypothesis statement that helps us to determine if it's a one-sided or two-sided. So it's all H1. And I have to tell you, I did a terrible job learning hypothesis testing when I was your age, because I don't know why we're doing that. I don't know it's related to confidence interval. I didn't know I can sketch it to find out where's my rejection area. So all I did was to memorize. When do I reject it? When do I fail to reject it? I just memorize it. So as soon as I barely passed that class, I forgot everything. Until I relearned this again in grad school, because there's a lot of application. We're not going to discuss it here, but there's so many discussion in the selection of alpha, so many discussion in performing hypothesis testing on multiple population parameters. So that's when I really start to learn this all over again. And I realized if you can relate that to a distribution, just sketch it. You know exactly based on your sketch, where is the rejection area? Where's the fail to reject area? Then there's no mistakes there. You don't have to rely on your memory. Okay? That's why we spend a lot of time here. All right. Now let's go over the second example before we take a break. Okay? Well, slow down here as well. The p-value really takes a lot of time to explain it, but I'd rather slow down, clarifies it, instead of leaving you with a lot of confusion. Okay, let's look at this one. In this experiment, we're making 15 drivers. So that 15 is my sample size. Perform 15 drivers are produced by a clock manufacturer, and we select the 15 randomly and calculate their coefficient of resistance. It is of interest to determine if there is evidence to support the claim that the mean coefficient of resistance exceeds 0.82. Okay, they always like to ask you if there is enough evidence to support the claim. By having evidence, that means does your sample average, if that sample average is consistent with your with what you believe the process is, or it is different from what you believe the process is. Okay, so that's my alpha. All right, I can simply give the question like this to you and ask you to derive your sample mean and sample standard deviation. But here we have it. All right, so let's go down to our hypothesis testing. I am going to start here. Let's perform our hypothesis testing. First of all, what is our parameter of interest? Don't underestimate the step because before when I put this first step into our quiz, you'll be surprised a lot of students doesn't even know what is the parameter of testing. Okay, so what is the main characteristics we care about here? In this case, this is our coefficient, mean coefficient of distribution. Now let's write down our null hypothesis and alternative hypothesis. Now this step is critical, so let's slow down here. H0 is what we believe the process is. Okay? Alternative hypothesis is what we're trying to prove. We believe our current process has the mean coefficient exactly at 0.82. Because what we're trying to prove here, sorry about the 0 and 1. This is 0, this is 1. The alternative hypothesis is what we're trying to prove. What are we trying to prove? The mean coefficient of redistribution exceeds 0.82. This is what we're trying to prove. Greater than 0.82. Okay? So in your homework, sometimes you'll see the null hypothesis written as mu less than or equal to. All the condition that's outside your alternative hypothesis. Okay, so you can write it as equal to or less than or equal to. Okay, let's start the testing. First, my alpha, in this case 0.05. Do we know anything about the population standard deviation? It was not given. This is unknown, which tells us this is our case number 2, and we're going to use t-distribution. Okay, now let's find out our critical value. In this case, one-sided. Upper bound. Okay, so this is the first example. We'll show you how to perform a one-sided confidence interval. So critical value is a singular. There's only one critical value. Okay, and I'm going to start our sketch. This is my t-distribution. This is a one-sided upper bound, so I have my critical value right here. Okay, the probability greater than this critical value is alpha. Now alpha over 2. So my critical value is positive t probability alpha, degrees of freedom, sample size -1, 15 minus 1, 14. Okay, so my critical value, let's derive my critical value. T positive 0.05, degrees of freedom 14. Okay, or we can derive that from using t value with a cumulative probability of 0.95, degrees of freedom 14. And I want to show you that on Excel. I don't remember if we've shown you the function of t, but let's go to that. Ooh, I forgot to pick a facilitator.
Professor Tara was the facilitator.
Oh, I did pick you. I'm sorry.
No worries.
Thank you. Just that's a test. I'm glad you remember that for me.
All right.
Okay, so let me know, Maria, if you can see my Excel.
Okay, I can't see it yet. I don't know if you started yet.
There you go.
I can see it now.
Okay, great, thanks. And so with a t-distribution, there's only 2 I want you guys to use. First one is T dot distribution. Okay, this is the function when you enter a T value, degrees of freedom. Okay, this is the T value. That's the distribution. True means it's a cumulative probability. This function will return a probability of your interest. Okay? The second one associated with T distribution is T dot INV. Consider that as an inverse, which means you have a probability. Typically, we use alpha because that's going to return the critical value for us based on our selection of alpha. And also, degrees of freedom. This is identical to your T table. If you remember on your T table, the top row is the probability of alpha. The first column is your degrees of freedom. So everything inside that table is T value, and that's the function to derive it. Okay? So where are we? In this case, in our example, our one-sided, our alpha is 0.05. Degrees of freedom is 14. And we want to, based on this value, we want to find our critical value. So I'm going to use this function here. Okay? So T dot INV, okay, cumulative probability to the upper bound is 0.95 because that leaves the probability greater than that critical value is 0.05. Okay, cumulative probability 0.95, degrees of freedom is 14. That returns our T value positive 1.76. Okay, I'll give you a minute to write down the function. I find it really helpful, but if you are used to use a table, feel free to use a table or your calculator is fine. Okay, when you write this down, I'm going to go back and write down this 1.75, and we'll continue. All right, let's go back to here. So I just wrote down the critical value based on our calculation. So this value is 1.76. I'm going to replace that with positive 1.76. Step 4, let's calculate our test statistic. This is our T statistic, and I'll show you the equation one more time, and I'll copy that to here. T statistic is very similar to Z. The only difference is that we use the sample standard deviation because the population standard deviation is not given. All right, I'm going to write it down over here so we can put this into your notes.
And instead of Z naught, it's just T naught, right?
Mm-hmm. Yes, the naught stands for test statistic. So we use that to differentiate all the critical values. Sample average, subtract what we believe the population mean is, divided by standard deviation, divided by square root of n. Okay, my sample average is here, 0.8372. And what we believe the population mean is 0.82. Divided by sample standard deviation, 0.02456. Divided by square root of sample size, 15.
Is that 0.62 or 0.02456? Right here, where your sample is at.
Yep, it's a 0.
Sorry.
Okay, real quick. Critical value. Actually, I will write this down here. So, critical value in Excel. I'm going to use this one. Okay. To calculate critical value, T dot I and V, enter the probability, in this case alpha, and your degrees of freedom, in this case 14. This will return the critical value. And keep in mind, if you put 0.05 here, what will return to you is this critical value on the negative side. Okay, things are since this is a upper bound one-sided question, we use 0.95 to return a positive value. Okay, so hopefully we don't have to switch back and forth. Everybody can look at the few notes and write down. Oops, sorry. Now let's draw our conclusion. Okay, our conclusion is to compare test statistic to critical value. Okay, my test statistic T, does it meet our, okay, my T statistic is here, a little higher than here, 2.72. This is my test statistic. Okay, my test statistic is outside my confidence interval. As a result, we reject the null hypothesis. Conclude alternative hypothesis. And what does this mean? Let's go back to the question. The question says, is there enough evidence to support the claim that the mean coefficient of restitution exceeds 0.82? Okay, based on our evidence on the sample, yes. Okay, so the mean coefficient of restitution exceeds 0.82. Okay, so that's our conclusion. I wanted to derive our p-value before we take on a break. Okay, so you can see how do we derive the p-value. Okay, I'm going to sketch this one more time to give you a better view. It's easier to explain p-value when you have a one-sided hypothesis testing. Okay, here is my test statistic. Okay, I purposely used the color that's consistent with here. Oops, consistent with Okay, this is my test statistic, 2.72. So this is my p-value. Not p over 2 anymore. This is p-value. Okay, I'm going to derive that. Also compare that to my alpha. So my p-value is the probability of t in this distribution greater than 2.72. Okay, so we can derive this from 1 minus the probability, cumulative probability of t less than 2.72. Okay, I'm going to derive this and real quick show you Excel. I'm going to share my Excel. Okay, so this is my test statistic, 2.72. Okay, and I wanted to derive the probability. Interesting. Okay, so I wanted to derive the probability of 1, subtract everything, cumulative probability below that 2.72. Okay, so here equal 1 subtract. How do we derive probability? Look at this one here. This is how we derive probability. Okay, so 1 subtract t dot distribution. What is my x value? That's my t value, 2.72. Degrees of freedom is 14. Cumulative probability. All right, I'll leave this here for a second. What are we deriving here? We're using 1, total probability of 1, subtract the cumulative probability from negative infinity all the way to positive 2.72. All right, so that'll give us 0.0083. I'm going to leave it here, give you a second to write this down while I go back and write down the probability. Okay, let's go back here. So that's my p-value. Compare that to my alpha. What is my alpha? Alpha is 0.05. Alpha is obviously greater, which means alpha is here, right? Further inside to give me a bigger area. So this is my alpha, okay? Which means my test statistic, 2.72, is located outside the confidence interval, okay? P-value is just a way to quantify the location of my test statistic using probability. So again, let's draw our conclusion. Since my p-value is less than alpha, we reject the null hypothesis, conclude alternative hypothesis. Again, I want to show you reject null hypothesis, conclude alternative hypothesis. Doesn't matter if you use the first method, comparing test statistic to critical value, or you use the p-value method, conclusion will be exactly the same. Okay, let's take a 5-minute break and come back at 11:15. You can stick around if there's any question. All right, I'm going to set up a 5-minute timer right now. All right, let's get back. Okay. So before the break, we pretty much covered all of the cases of performing hypothesis testing. Don't let it overwhelm you. There's only 2 cases. Okay, there's only 5 steps to perform hypothesis testing, and the 2 different cases only applies on step 4 when we derive the test statistics. When there's no when the population variance is not given, we use the t statistic. When population variance is given, then we use the z statistic. Okay, and go over the question carefully and find out if you're establishing a one-sided or two-sided hypothesis test. That's all. That's all. So after that, I think what's most helpful for you is to go down as many exercises as we can. So I have about 4 other exercises I want to go over together. I also want to show you how do we do that in Excel as well. Excel makes the calculation of finding the z-value, finding the t-value, and their associated probability a lot easier. But Excel are just blank cells. So when you want to use Excel, you really want to be very clear about the different steps we're performing. So for the first example, I'll just carry out each steps manually. For the second example, since we have to calculate this sample mean and sample standard deviation, I'll carry out this calculation in our Excel. Okay. And looks like there's only 4, but to explain that still takes some time. Okay, so for the first exercise, inspector of flow metering device is administrator. They're performing a hypothesis test to see if the actual mean flow rate is different from the setting. So this is what they believe the process is currently at. And they wanted to prove based on the sample of 25 and the sample average. Sample average is here to see if the claim is still true. Is the actual process was able to maintain that setting at 200 milliliters per hour. Okay, so I'm going to highlight this 12 milliliter is my population standard deviation. Okay, so in this case, population standard deviation is given. Okay, based on this information, we know we're going to use a z distribution. Okay, so let's start it. First of all, what is our parameter of interest? Our parameter of interest is the flow rate. Okay, number 2, what is the null hypothesis? Okay, again, we wanted to see if the actual average flow rate meets the setting at 12 milliliters per hour. So we believe our current process flow rate is exactly 200 milliliters per hour, while the alternative is what we're trying to prove. Hypothesis determining whether this is different from, not equal to. I derived it from here, different from the flow rate setting. Okay. Step 3, let's calculate our critical, let's find out our alpha. Alpha is 0.05, so my critical value. This is when I start my sketch. Okay, we know this is a z distribution. We also know this is a two-sided hypothesis testing. I have 2 critical values. Okay, alpha is 0.05. I'm going to skip a step. My 2 critical values are plus minus 1.96. If you wonder why, go back to our very first example. Okay, so this is negative 1.96. This is positive 1.96. Okay, step 4. Let's calculate a test statistic. My z-test statistic is the sample average, subtract what we believe the population mean is, divided by sigma, divided by square root of n. Sample average is 205 milliliters per hour. Subtract we believe the population mean is 200. Divided by population standard deviation is given 12. Divided by sample size. Okay, that is my test statistic. Okay, here my test statistic is 2.08. Okay, again, now let's see where is that corresponding to my confidence interval. 2.083 is over here. Okay, let's draw our conclusion. It is outside my confidence interval. Okay, my z statistic is greater than positive 1.96. As a result, we reject the null hypothesis, conclude alternative hypothesis. Okay, don't forget the most important thing, our interpretation. The mean flow rate is different from the setting. Right? That's the conclusion from our analysis. But what are you going to do after you make the decision? We confirm that there is a significant differences between your actual flow rate versus your setting. So we have to put in some efforts to bring them close. Our actual flow rate should follow what our setting is. Okay, what caused that differences? What can we bring it back? What are we gonna do with the current process? Okay, so a lot of decision has to make after this conclusion being made. So very important to tell exactly what is the conclusion. Okay, real quick, let's calculate the p-value. Okay, I'm going to sketch this one more time. This is my z. My test statistic is 2.083. So this is my p over 2 value. Don't forget, this is a two-sided hypothesis testing. So my p over 2, so my p-value, let's go direct to p-value. My p-value is 2 times, okay? 1 subtract cumulative probability to 2.083. Okay, let me see. Hopefully this is clear to you. What is this part? This is the cumulative probability from negative infinity all the way to 2.083. 1 subtract that is the green area. Why are we multiply that by 2? Because it is a two-sided hypothesis testing. Just like our alpha, we have another p over 2 on the left-hand side. Okay. Okay, so okay, I did a calculation real quick in Excel, and that p-value is 0.0372. Okay, this value obviously is less than our alpha. Alpha is 0.05, okay, which means my alpha is here. Higher, greater area than my p-value. Okay, which also means my test statistic is located outside the confidence interval. Okay, p-value less than alpha, we reject the null hypothesis. Conclude alternative hypothesis. That mu is not 200 anymore. Okay, again, reject null hypothesis. Conclude alternative hypothesis. Doesn't matter which method you use, they should be identical. Okay? I'll give you a minute, then we'll go down to the next exercise. Okay, let's go down to the next exercise. Okay, next exercise. In this case, let me zoom in a little more. And okay, studied the white blood cell recovery of patient who went through a chemotherapy treatment, and they counted the recovery in number of days. So now they've observed the next 19 patients, and here are the number of days for their white blood cell recover to the normal level. It's listed over here with 19 data points. So question 8, is there sufficient evidence to support the claim? What are we trying to prove? That the mean white blood cell exceeds 12 days. So this is what we're trying to prove. And the second one, construct a two-sided confidence interval. All right. So we'll first show you step 1 and 2. From step 3, we'll move to Excel to show you how do we carry out calculate a few statistics using Excel. So first, let's carry out our hypothesis testing. First, what is our parameter of interest? What is our mu over here? It's not white blood cell count. It is the number of days of recovery. Okay, so this is our white blood cell recovery days. Okay, let's write down our hypothesis. What we currently believe recovery day takes about 12 days. because question A tells us what we're trying to prove is that recovery date exceeds 12 days. Right? You can write a null hypothesis as less than or equal to, if that makes more sense. Well, either way, we will only conclude one of the two statements. Step 3. Step 3, let's calculate our critical value. First of all, do we know anything about the population standard deviation? No, I don't see anything about the population standard deviation. Okay? Population standard deviation is unknown, which means we are going to use the Z distribution. Okay? So what is our critical value? Our alpha is not given, is it? Let's use 0.05. I do want to use 0.05 is because this is a one-sided hypothesis testing. But if you look at the second question, it's a 95% two-sided. All right, I do want to show you the differences of using one-sided and one-sided hypothesis testing and two-sided confidence interval. Okay, so let's find out the critical value. Okay, in step 3, we'll find out the critical value and we'll determine the rejection area or rejection criteria. And number 4, we're going to calculate the Z-test statistic. Number 5, we'll draw conclusion. Okay, from this point forward, I'm going to move to Excel. All right, let's go to Excel. Okay, Maria, can you see my Excel?
Yes, Professor, I can see it.
Great, thank you. Okay, so this is our question. That's our 19 patient. I've derived the sample average and derived the sample standard, that's the count, sorry, and sample standard deviation. Don't forget, the very first thing we've taught you in this class is how do we derive the sample standard deviation. Use the .s for sample standard deviation. All right, so we're going to carry on to step 3 here. We're going to calculate critical value based on our degrees of freedom and alpha. Okay, so I'm going to start deriving the critical value. If you recall previously, this is a t-value. Okay, we're going to enter a probability and return the t-value. So here I'm going to use the t dot inv function. Okay, sketch this. And you know, sketch the t-distribution. You know, this is a one-sided upper limit critical value. Okay, if that part's not clear, let me know. I can always go back and sketch it on our notes. Again, this is a one-sided upper bound critical value. Okay, so my probability is 0.95. Degrees of freedom is sample size minus 118. That's my critical value. Again, I'm going to slow down again. This is my, I use the TINV function because I have the probability. Probability is my alpha. I also have the degrees of freedom. What I don't have is that critical t-value. So I'm going to input the probability. And here I've entered the cumulative probability. Right? The degrees of freedom is my sample size 19 minus 1. That gives me my critical value. Okay? How am I, so what is my rejection criteria? When are we going to reject it? When my t statistic is greater than 1.73, positive 1.73, we will reject the null hypothesis. Okay? As That's my rejection criteria. Let's go down to step 4. Step 4 is where we derive the test statistic using our sample information. Okay, I already derived the sample average and the sample standard deviation. We're going to need that in this step. If you recall, our t statistic, the numerator was sample average, subtract what we believe the population mean is, 12 days. The denominator is sample standard deviation divided by square root of my sample size, 19. Is there any question? The numerator is simply my sample mean, subtract our hypothesis test value, 12 days. Denominator, since population standard deviation is not given, we are going to use the sample standard deviation divided by square root of sample size. Okay, so that's our test statistic. Did my test statistic meet my rejection criteria? My test statistic is actually less than 1.73. It does not meet my rejection criteria. Okay, because of that, we fail to reject the null hypothesis. In other words, we conclude our null hypothesis that my recovery date is 12 days. All right, so I do want to show you the Excel part, but Excel are just blank. So you need to have a very clear mind about where are the steps, what do I need in this step, and don't confuse test statistic with critical value. Okay. Next, let's derive the confidence interval. Okay, if you recall previously, we're going to calculate a 95% two-sided confidence interval of the mean. Okay, so let's calculate the upper bound. How do we derive the upper bound? Sample average. Sample average is here. Plus my t statistic. In this case, we cannot use this t statistic anymore. Does anybody know why? Why can't I use that test statistic calculated earlier? I'm gonna go back to here in a second.
Is it greater than? I didn't. I think it's greater than the t, right?
So over here, what we set up is a one-sided hypothesis testing. So our t critical value is exactly alpha, and then n minus 1. But with a two-sided, our alpha, our t statistic is alpha over 2. Okay, that's what I want to show you in this exercise. In our hypothesis testing, we're simply doing a one-sided hypothesis test with a upper bound. And that upper bound critical value is t alpha n minus 1. In this case, we're calculating a two-sided confidence interval. So this is my t. That's my lower bound. That's my upper bound. Okay? The probability here is alpha over 2. Alpha over 2. So we can derive a lower bound and upper bound. So this part is my t minus t, alpha over 2, and minus 1. Here is my positive t, alpha over 2, and minus 1. Okay? So be very clear about if you're calculating the one-sided or two-sided. Here it tells us specifically to calculate a two-sided confidence interval. Okay, So it's just a variation, but it's mainly to see if you understand the different concept of one-sided and two-sided. So if in your homework you're not sure if you're testing one-sided or two-sided, always clarify it with me before you approach it. Don't make any assumption. Okay. So I'm gonna go back to here. I'm gonna go back to my Excel. Okay, I'm glad some of you are staying on top of this. Okay, so for this, before I go to the upper bound, I think it'll be better to establish our p-value. Our one-sided t-value one more time. Okay, so my t 0.025, sample size minus 118. Let's derive that value. Okay, so here we're going to return a t-value given a probability, right? We have the probability, returns the t-value. So again, we're going to use the t, I, and v function. Probability is alpha over 2. You can either use 0.025 or 0.95 over 2. Degrees of freedom is 18. Okay? I can either use this one to get a negative value or 0.95 divided by 2, 18. That's going to return the positive. What's going on? Didn't take it as 0.95, did it? Why do I get different values here? Hold on one sec. It doesn't give me the same value. Somehow I messed it somehow. You're right. 0.975. Thank you. One subtract this, right? Oops. What was I doing? That gives you the negative one. This gives me the positive one. Okay? 1 minus 0.025, 18. Thank you. All right. So the upper bound is my sample average. Sorry, I'm going to use equal and click on my sample average here. Plus my t-statistic multiplied by my standard deviation. Standard deviation is here divided by square root of my sample size. Okay, that gives me the upper bound. So this part is my sample average. This part is our estimation here. Okay, t statistic multiplied by sigma divided by square root of sample size. Okay, lower bound. Okay, same thing. Sample average. Subtract. T statistic multiplied by standard deviation divided by square root of my sample size. Okay, so that's how we derive the upper and lower bound. I am going to focus on here so you can see the equation. And we'll go down to, let me see, I think we have time to go over one more example. So hopefully by now you'll see we follow exactly the 5 steps. things to look out for is how you set up the alternative hypothesis based on the problem description. And based on the problem description, you will also calculate different test statistics. And another thing to look out for is how do you draw your conclusion. Okay. Go back to here. (150). The cooling system in the nuclear submarine consists of a assembling of welded pipes, and they want to test the strength of welding, and it must meet or exceeds. Must meet or exceeds 150 psi. Okay, alpha is given. How do we verify that that statement? We have to collect actual sample. 20 samples, average is here, and sample standard deviation is here. Perform hypothesis testing to see if the process meets the specification. Okay, so specification is the requirement. We need the process to meet this requirement, but what about our actual process? Does it actually meet the process or it doesn't? So we'll find out using our hypothesis testing. Okay, hypothesis testing. First, our mu is the weld strength. Number 2, let's write down our null hypothesis, alternative hypothesis. Null hypothesis is what we believe our current process is. And we believe our current process is meeting the specification. Specification says the strength must meet or exceeds, equal to or greater than 150 psi. Okay? When would it not meet the specification? So our alternative hypothesis is to prove it does not meet the specification. Okay? So my mu is less than 150. Okay, so this part means we meets the specification. Meets the spec. While the alternative means we do not meet the specification. Right? Very important. Step 3. Do we know anything about the population standard deviation? No, population standard deviation is unknown. So in this case, we'll use the Z distribution. Oh, sorry, T distribution. Okay, alpha is 0.05. One-sided lower bound based on the way we write our alternative hypothesis. So I'm going to sketch it and let's derive the critical value together. T distribution, lower bound. Okay, so this is my one-sided lower bound. We know this probability is 0.05. Critical value is negative t. Probability is 0.05. Degrees of freedom is sample size 20 minus 1, 19. Okay? So here's my critical value. Singular. Okay? Let's go to my Excel. Okay, so we're deriving t, negative t value, 0.05, one-sided. Degrees of freedom is 19. This is the value we're trying to derive. Excel doesn't want to type text. So it's So we want to find out the t value. We have the probability, we have the degrees of freedom. We're going to use this function. All right? Equal t.inv, probability is 0.05, degrees of freedom is 19, right? So that returns the critical value. Negative 1.7, let's run it up to negative 1.73. Okay, actually, I'll give you a minute in case you need to write this down. I'm going to go back and write this down first. Okay, let's go back to here. Once we've established our critical value, what is our rejection area? When will we reject the null hypothesis? We'll reject the null hypothesis when our test statistic from the sample fell outside the confidence interval, right? So when my t-test statistic is fell outside, below the lower bound, below the negative 1.73. All right? I don't think we would. If you look at the sample average, number 4. Okay, let's calculate the test statistic. Okay, T, sample average 153.7, subtract 150, divided by sigma, S, sample standard deviation, 11.3, divided by square root of 20. Okay, so that's my test statistic.
Let's say 153.7.
153.7. 153.7, that's the sample average.
Okay.
Interesting. Okay, so let me do a quick calculation over here. Subtract 150 divided by square root of 20. Oops. Okay, 1.46. 1.46. Okay, where's my 1.46? 1.46 is positive on the right hand side. 1.46, right? So it's well within the confidence interval. 5. So since my test statistic is greater than negative 1.73, we do not meet the rejection criteria. In other words, we fail to reject the null hypothesis. In other words, we conclude the null hypothesis that our current process, the welding strength, is greater than or equal to 150 psi. Okay, what does that mean? The current process. The specification. All right, really important. We collect a few samples to confirm our current process still meets the specification. Continue the production. Everything seems to performing well. All right. So went through about 7 different exercises with you guys today. Hopefully you guys start to see the patterns now. There's only one question I was not able to cover today, but go ahead. Give it a try on this exercise 160. Okay, formulate your hypothesis testing. Perform the test. I want to see if you can calculate your own p-value. Okay, don't worry about the other exercise because we're going to come back and go over this next time. You should have all the information to start working on your homework today, but it's not due until next week. Sorry we went a little over time, but you can stay if there's any question. If not, feel free to log off. Have a nice weekend. Enjoy your not so excited Halloween. I'll see you next weekend.